Okay, welcome to the lesson on descriptive and inferential statistics. So, descriptive statistics versus inferential statistics. What's the difference? What can we use each one for? Descriptive statistics, as you might imagine, are used to describe the shape or scale of a data distribution, and they can be used in the case where you only have one group of data, or they can be used with multiple groups to describe each group individually by itself. And some examples of descriptive statistics would be the proportion of test subjects that fall within a certain response category. For example, the pie chart here could represent that 10% of the children that you see out of a certain population have already experienced caries in two or more of their teeth by a certain age. And then we can have measures of central tendency, and those tell you where the middle of the data distribution are. So there are several different measures of central tendency. One is called the mode. One is the median. One is the mean. There's even others that are less common, such as the characteristic strength or characteristic lifetime of a group of specimens. And so, for example, in the histogram of data shown here, the mode would be the response that occurred the most frequently, the highest bar on the graph. So that's one measure of central tendency. And the median would be the point below which 50% of the data fall and above which 50% of the data fall. So that would be the median. And the mean would be the average of all the data points. So that may be somewhere in between the other two. Depends on the shape of the distribution. And then we can describe also the variability in a result. So, for example, standard deviation or standard error would be measures of how far the data are spread out, or they all clump together into just a couple of really tall bars on the graph. Another measure that you may not have heard of is coefficient of variation, which is just the standard deviation divided by the mean. And that's a measure of variability used for comparing different groups that have very different means and making a more fair comparison between them. So those are the descriptive statistics we encounter most commonly. And then there's inferential statistics, which allow us to test a hypothesis. And they're typically used to test for differences between groups. For example, you could have a method of performing oral surgery that's a traditional method, and then you could have another experimental method that we think may perform a little bit better for the same oral surgery, and try those two methods on two different groups of people, and then test something like how well their jaw fits together after the surgery, or how satisfied the patients are with the surgery, how much pain, self-reported pain they experience, something like that. And so a inferential test would test whether the difference between the means or the medians, the centers of these groups, is a significant difference, or whether it's a difference that might have come from just random variation. And then another case is if we don't have our data organized neatly into two or three groups, but we have a bunch of different levels for one of the variables that we're trying to test, then we can use regression to model how one variable varies with respect to another variability or correlation, and that's a form of inferential test too. So all of these statistics, the descriptive and the inferential statistics, come in two flavors. One of them is a statistic that you are 100% sure of, and that's when you use the statistic to describe or inference on the samples that you performed an experiment or an observation directly on, a sample being a small group of patients who you're observing. And the other flavor that the statistic comes in is what you would predict based on your measurement of your small sample, what you would predict would be the response for that statistic you would get from the wider population. And there will be less than 100% ability to predict the way that the wider population would behave based on observations of a small sample from that population. And so that means that we have confidence intervals. We can calculate for sure the proportion of children that fall within a certain category in our study. We know that exactly 10% of the children had that response in our study. But if we try to estimate based on that, how many children in the entire city of Jackson are going to fall within the same category, we can make an estimate, and there are formulas to calculate what interval we would be 95% sure the true answer would exist within. And for example, that would be called the 95% confidence interval. And there's other types of other sizes of confidence intervals with different levels of confidence that we could calculate. But in medical research, 95% is by far the most commonly used. So we have these descriptive statistics and inferential statistics, and we would like to use them to describe and draw inferences on different response variables that we have in our studies. And which statistics we're allowed to use depend on the type of response variable that we're describing. So we need to talk a little bit about the different types of response variables. They're typically broken down into the types of nominal, ordinal, interval, and ratio. And one reason for choosing these names is that it helps with a mnemonic device that they spell out noir, which is the French word for black. And even in the United States, among native speakers of English, most people have heard the word many times and can remember it. So first of all, let's take a look at nominal variables. What makes a nominal variable? So the different levels or answers to a nominal question are names, but they have no particular order. So one of them isn't necessarily greater than another one. In other words, if you had possible responses from your patients that were numerical, 1, 3, 5, where 5 would be greater than 3 and greater than 1. That would not be a nominal variable. So what would be a nominal variable? Political parties, genders, religions, color hues. And by color hues, what I mean is, color is particularly important to dental research. So what I mean by color hues are basic groupings of color, like brownish colors or grayish colors or yellowish colors. When we have dental prosthetic materials, they are usually ordered from the dental lab by placing a prescription in terms of these different hue names. And we have shade guides that allow us to compare a tab of material against a patient's tooth and determine which color hue category it falls within. So none of these would be greater than another one, but later we will come to a different type of color variable where we can have some greater than and less than each other. And another example of nominal variables would be diagnostic results where you could test positive or negative for a disease or a condition. Like a tooth could test positive for having caries, uncavitated lesion, you might want to test. Or if you had a accidental needle stick while treating a patient, you might want to go get tested to see if you're HIV positive. So that's the type of test result we're talking about. And some examples of the values those variables can have: yes and no answers are really common nominal variables, or they could be that your patient's either on an experimental treatment or a benchmark treatment that is one already commonly used that we know how it works, or a placebo treatment. And what type of descriptive statistics are we allowed to use? For the central tendency, we can only use the mode for nominal variables. So whatever answer occurs most commonly. We're not allowed to use the median or the mean for a nominal variable. We can also use proportions, which tell what percent of the answers fall into each category. And then we have a variety of statistical tests. We can use chi-square, binomial test, Fisher's exact test. We have another lesson towards the end of the course. Well, we'll go into some of these in more detail. But in general, I don't want you to know all the details of exactly which statistical test is appropriate for a given situation and how to calculate that test. Because you have people like me or statisticians to ask about those things throughout the curriculum and later in your career, and there's statistical software to do the calculations for us. So we won't go into too much detail on the tests. And then there's sensitivity and specificity, and it's really important for all healthcare providers to understand the concept of sensitivity and specificity and how the calculation is done. So in this lesson, later in this lesson, I'll go into more detail on that. Then we have variables that are in the category of ordinal. So what makes something ordinal is the groups are still categories. However, they have a rank order where one is greater than another one. And again, we're still not talking about counting numbers where we know exactly how much greater the higher value is than the lower one. We're not talking about knowing that one patient has a score of 5 and one has a score of 9, so one is 4 more than the other one. For ordinal responses, a better example would be military ranks, where we know a sergeant is higher ranking than a private, but it's hard to quantify that, and we can't really say whether that difference is the same as the difference between a general and a major, or if one is twice the difference of the other one. We don't really have a way to quantify that. So that's an ordinal variable, is that they have a definite ranking from high to low, in the possible responses, but we don't have a idea of how far apart the responses are on a scale. Levels of education: associate's degree, bachelor's, master's, PhD, professional doctorates, and so on. The Likert scale occurs very frequently in dentistry and medicine, and that's a scale where you ask the patient to do something like report how they're feeling today. And that's another example of a scale that could fall under ordinal or under interval data. It depends on how you ask the question. If you're feeling really poorly or fair or ecstatic, these would be non-quantitative, but they would have a definite rank to them, so they would be ordinal. Or maybe you've encountered the Likert scale more frequently in the form of questionnaires where they ask you if you're extremely dissatisfied with your service, or moderately dissatisfied, or neutral, or satisfied, or extremely satisfied. So that would be a Likert scale, and it would be a ordinal response. Mohs hardness. We know that diamond is harder than sapphire, and we know that sapphire is harder than talc. But because that scale is not a linear scale, we don't have, we can't subtract those values to find out exactly how far apart in hardness they are, unless we use a different type of hardness scale. Okay, we come back to the topic of color, which is a frequent and very important topic for dentists. And color is measured not only in terms of hue, but in terms of value and chroma, where value is the brightness of, a low value color would be black, and a high value color would be white. And if you happen to have a color hue that was gray category, then how bright the gray is would tell you whether you had a high value or a low value. Now, we could assign an interval, a very detailed quantitative number to value. We have ways to measure that. However, that's not the way it's usually dealt with in the dental clinic. Again, we have a shade guide which has just a few categories of value on it, and typically they would be low, medium, and high, or 1, 2, and 3, where the difference between 1 and 2 wasn't a quantitative one. And then with colors, we also have chroma, which is the amount of saturation of the particular hue, where, for example, you could have a yellow hue, and if you had a low chroma, it would look like yellow with some gray in it. And if you had a high chroma, it would be a very bright, vivid yellow. And so the degree to which a color is saturated, or its chroma level, is a number that's a value that could be measured numerically with great accuracy, but in the dental clinic we usually deal with a low, medium, high type of classification. So examples of responses that are ordinal could be, as we mentioned, you disagree, you're neutral, or you agree with something. Patient's condition: good, fair, serious, critical. We know one is better than the other, but it's hard to quantify exactly how much. Now, what descriptive variables are we allowed to use for ordinal responses? We can still use the mode, but now we gain the ability to use the median as well. And so that, again, is the point where we're in the middle of the data set. We have some new statistical tests that are available to us. We can use the Mann-Whitney U, the Wilcoxon signed rank, The ANOVA on ranks, if you have looked in the scientific literature somewhat already, you'll know that ANOVA is a very popular test. ANOVA on ranks is a somewhat lesser version of that than the traditional ANOVA, and you see rank here again. So often the statistical tests that we use with ordinal variables are called ranked tests because we just keep track of whether a response is in first place, second place, third place, fourth place, and so on in terms of ranks when we do the calculations in the software instead of having exact numbers that we can compare. Now, coming to interval data. Interval data, now we have quantitative numbers and they have an equal interval between the numbers on the scale. So if we were counting 1, 2, 3, 4, 5, 6, and we knew that the difference between 2 and 1 was equal to the difference between 3 and 2, then that would be interval data. It has equal intervals. And but however, the interval data doesn't necessarily have a important reason for the point of the 0 on the scale. So it can be an arbitrarily chosen 0. And this is a disadvantage to some point in the data because it means that we can't multiply and divide and make judgments about percentages of the mean or median in the data. So an example would be the Celsius or the Fahrenheit temperature scale, where we know that that the difference between 10 degrees and 0 degrees is equal to the difference between 80 degrees and 70 degrees. But we also know that we can't necessarily say that 80 degrees has 8 times the amount of heat content that 10 degrees does. So it's an arbitrary 0 point instead of being absolute 0. And we can't multiply and divide, only add and subtract in intervals. IQ is another example, and then more detailed Likert scales where we ask someone to rate their current pain level on a scale of 1 to 10 would be an interval, because we're assuming that if they put 3 instead of 2, that's equal to the change that they would be expressing if they said 2 instead of 1. So an example of interval data would be you could have a patient with a value that's 20 less than the mean for the group of patients. And when we have interval data, now we have open to us a wide variety of descriptive statistics. We have the mode and the median again. Now we can have means, standard deviations, standard errors, and coefficients of variation, which again is the standard deviation divided by the mean. We have more advanced tests we're allowed to do with interval data. So we can now do correlation between two different interval variables. We can do regression analysis, an independent t-test, a paired t-test, which we would use in the case of before and after data on the same test subjects, and the regular analysis of variance that's so popular. And then the last type of data that we have is ratio data. And it's called ratio because we are allowed to subtract, we're allowed to multiply and divide. So we can say that one patient has twice the value as the mean, and one has half the value of the mean. And ratio data, the difference between them and interval data is they are on an absolute scale. So something that has a height of 0, that means it has no height at all. So that's a meaningful point to put 0 on the scale. Same thing, absolute temperature, absolute 0 degrees Kelvin, for example, would be a substance with no thermal energy in it at all. And now we can talk about something being a certain proportion of the mean of the rest of its group. we have all the same type of descriptive statistics and inferential statistics that we can do between interval and ratio data here. One thing I want to point out is that an old method of classifying types of data calls for not interval and ratio, but integer and continuous data, where integer values cannot take on fractional values in between, don't have an infinite number of values in between any two values, and continuous would have that. That's not according to the Noir organizational system, and I think Noir is better, and most people do now. It's by far more commonly used. So don't be confused when you see the I. The I refers to interval and not to integer. There's a particular type of test statistic that is used with nominal data, and it's one that is important for all medical professionals to know in detail, and it's one where a lot of miscommunications and patient anguish have been caused by medical professionals who don't understand it properly. And that would be sensitivity and specificity. These come in when we're talking about the ability of a diagnostic test to perform correctly. So the sensitivity is the ability to correctly detect a condition. So if the patient has caries in a tooth and you do a test with high sensitivity, then and it comes back positive, you would say, well, I'm very confident that this patient has caries in that tooth. But if it was a test with low sensitivity, then you may not really have an idea or not after conducting it whether the patient has caries in that tooth. And you can also think of it as the chance of avoiding a false negative. So it's the ability to correctly detect a condition, or the percent chance. It's expressed usually as a fraction or a percentage of 100%. And it's the percent chance of avoiding a false negative, of failing to say that the disease or condition is there when it's really there. And then the other one is specificity, and that's the ability to correctly deny a condition, or to say that the condition is not present when it's really not present. So you can think of that as the chance of avoiding a false positive. So a person is not HIV positive, and they take the test, and it may say that they're HIV positive, and that would be a false positive. And so obviously we would want the specificity to be very high, like 99% or so that we could easily avoid false positives. If the specificity was 99%, then the chance of having a false positive would only be 1%. And here's a table to kind of illustrate that for you. That if the disease is absent and the test gives a negative result, then it's a true negative. But if the disease is absent and the test gets a positive result, then it's a false positive. And we can calculate the specificity of a test by taking the number of true negatives and dividing it by the total of true negatives and false positives. So A over A plus C is the specificity. Now, if the disease is present and we don't detect it, then that's a false negative. So we don't want to be in this quadrant. But if the disease is present and we do detect it, that's a true positive. And the sensitivity or ability to detect a test is the true positives divided by the total of the true positives and the false negatives. So D over B plus D is the sensitivity. A non-cavitated carious lesion, you could do that by a visual exam, and the visual exam might have a poor ability to detect caries when it's actually present, so it would have a sensitivity, say, of only 38%. But the visual exam would stand a low chance of accidentally saying caries is present when it's not, so you wouldn't drill and fill a tooth that didn't need it. So that's very important, obviously, to have a high specificity, and a visual exam might have a high specificity, like 99%. Transillumination of the tooth might have a better sensitivity, much better sensitivity, and a slightly worse specificity. Taking radiographs, using laser illumination, electrical conduction, so we have a lot of different types of tests we can perform. And you might think that if you're ultra conservative and go for the test with the specificity of 99%, and you think, well, I might miss caries when it's present, but the patient will come back in 6 months and I'll get a better chance to detect it again, and hopefully we'll have very few cases where I fail to detect the caries before it becomes quite severe. And so maybe if you're going to be conservative about your practice, you would like to use a method that has a 99 or a 97 or 96% chance of avoiding false positives. And you might think 99 is a really high specificity, and well, it is high, but you might think that that automatically means that if you that you would only have a 1% chance of failing to have caries if you get that negative test result. And that's not actually the case. Specificity is not tell you the probability of having the condition. And sensitivity does not tell you the probability of having the condition. They only tell you the probability of correctly identifying the condition. And the probability of having the condition, given a positive or negative test result, depends on how prevalent that condition is in the population, in addition to depending on the sensitivity in the American. He says, suppose that you have a population of 10,000 patients, and then you have a disease that only exists in 1% of the population. So out of 10,000, there are only 100 diseased individuals, and 9,900 are not diseased. And then suppose you test for the disease using a test that has a sensitivity of 99%. And so out of the 100 who are diseased, only one of them will you fail to detect, and you will detect 99 of them. And suppose the test is a wonderful test, and in addition to having a sensitivity of 99%, it also has a specificity of 99%. And so out of the 9,900 not diseased individuals, only 1% of them, or 99 of them, will return false positives. Then the question is, given that you test positive, and this could be something with a very important answer. For example, I have never seen a dentist as worked up and concerned as the dentist I met on the elevator at our school one day, who had been working and had had a needle in a patient who was known to be HIV positive, and accidentally stuck herself with that needle. And as somebody who's going to be working with people with a variety of conditions, or being looked up to as someone who understands science by your friends, and they may want you to explain to them the meaning of different test results they have. And so something like a test as to whether you're HIV positive after an incident like that can be a very important and distressing question. So you might wonder, well, given the fact that I test positive, what's the probability that I actually have the disease? And surprise, the answer is not 99% chance that you have it, given that you've already tested positive. Because out of all the people who test positive, there were 99 who had the disease, 99 who didn't, for a total of 198. And so the chance, given that you've already tested positive, the chance that you actually have the disease is 99 divided by 198, or 50%. And this happens because the disease we're talking about in this example is fairly rare among the population. If you had a disease like caries in a particular tooth that's more common, then there wouldn't be such a wide difference between the sensitivity and the chance that the condition was actually there, given that you have a positive test. Of course, we will have another lesson where we talk about proper methods of sampling populations and the appropriate statistical tests to put those samples to when you're developing your research proposals. But that'll be our statistics for now, and that prepares you for the upcoming lectures on critiquing studies and systematic reviews of the literature. I'd like to remind you that there are quizzes online associated with each lesson, so please take the online quizzes to convince yourself that you have gotten all the important points out of this lesson. And if you haven't, then please feel free to go back and listen to the lesson and take the quizzes as many times as you need to. And when we come to class, please come prepared to discuss the previous two lessons, the observational studies and the statistics lesson.